We have just derived the equation for the thrust force of a rocket that ejects mass at a velocity v and at a rate m dot. A very important result can be obtained by working on this equation a bit. This is an important video because we will introduce some key concepts of rocket propulsion that you will use later on. Let us assume that v is constant. In other words, that the exhaust velocity of the jet is always the same. We fire our rocket in empty space for a time interval from t0 to t1, and we want to find out what are the effects of this maneuver. Now remember that m dot is the rate at which we eject a mass, so it equals the rate at which the rocket is losing mass. If we write m dot as minus the time derivative of the rocket mass, we have this equation. Integrating, that means that the rocket mass loss from t0 to t1 is simply this one. Going back to thrust equation and substituting m dot, we can also easily integrate in time by rearranging the terms like this. On the other hand, the integral in time of the acceleration from the initial time t0 to the final time t1 is the change in velocity of the rocket, v1 minus v0. We call this velocity increase the delta v of the rocket maneuver, and as we will see later, it is a very important magnitude. For every maneuver that we want to perform in space, there is a fixed known cost in terms of delta v that the rockets of the spacecraft have to provide. More ambitious maneuvers require higher delta v. For example, transferring spacecraft from one orbit to another requires a certain delta v that depends only on the initial and final orbit, and on the path chosen for the transfer, of course. Keeping the desired position in the orbit by compensating perturbations also requires some delta v per year. Traveling to the Moon or to other planets requires a considerable delta v. Lifting a payload from the ground and inserting it into orbit also can be expressed in terms of delta v, and so on. On the other hand, the integral on the right-hand side is the natural logarithm, so we have ve times logarithm of m1 minus logarithm of m0. What is the same, applying the properties of logarithms, we have plus ve logarithm of m0 over m1. Combining all this, we reach this final equation here. This is the famous rocket equation, or Tsiolkovsky's equation, after the Russian scientist who derived it for the first time, toward the end of the 19th century. This equation allows us to calculate the delta v that shall obtain if we burn and eject propellant at exhaust velocity ve until the rocket total mass has decreased from m0 to m1. We can see in this equation that the larger the velocity ve and the mass ratio m0 over m1, the larger the delta v we get. Note also that a variable has disappeared from the equation, the time. The rate at which we eject the propellant, or the time we take to do the maneuver in empty space, is completely irrelevant from the viewpoint of the delta v that we obtain. Only the final mass ratio, m0 over m1, is important. This means, in particular, that we can switch on and off the rocket as many times as we see fit. The total delta v that we obtain for the duration of its mission is the same and depends only on ve and the mass ratio, m0 over m1, when all the propellant has been used. Once the delta v that we have to achieve in a given mission is known, we can see that the higher the exhaust velocity ve, the less propellant we have to use. That is, m0 over m1 doesn't need to be so large. That means the larger ve, the smaller the rocket needed for a mission. This can be better appreciated if we rewrite our equation as shown here. We have simply inverted the logarithm as the exponential function, and we have solved for m1 over m0. Suppose that we want to put a payload into orbit, for example a satellite, that weighs 1 ton, that is 1000 kilograms. This is the final mass in orbit, so m1 is 1000 kilograms. The delta v to go to low Earth orbit at 400 kilometers altitude is about 10 kilometers per second. If the VE of the rocket is around 3 kilometers per second, which is a common value for chemical rockets, as we will see in the next video, then the final to initial mass ratio is only 0.036. That means that only 3.6% of the initial mass of the rocket on the ground is the actual satellite, and the remaining 96.4% is propellant that we burn in the way up. The initial rocket has to be 28 tons, including the satellite, to manage this. Note, however, that we have neglected the structural mass of the rocket in these calculations. The typical cost of sending 1 kilogram of mass to orbit is about 20,000 euro with the current technology. I want you to appreciate the difficulty of space travel with this equation. The exponential function in the equation is basically telling us that if the delta V of the mission is quite larger than the VE of the rocket, then m1 over m0 becomes quite small. The physical reason behind this is the exponential, and when we have to accelerate propellant with us until we use it, so the mass of this propellant adds to the payload in Newton's equation until we eject it. This has dramatic consequences. For example, in order to achieve ambitious missions like going to Mars or other planets, which require a lot of delta V, we need rockets with V in the order of the delta V that we want to achieve if we want to have a launcher of a reasonable size. Otherwise, the initial mass of the rocket simply blows up and the mission becomes unfeasible. Different rocket technologies have different values of VE. In fact, the exhaust velocity is one of the main figures of merit of the rocket. It is so commonly used in the aerospace world that we even have a fancy name for it, the specific impulse. The specific impulse of a rocket is nothing else than its exhaust velocity VE divided over a constant, g0, the gravity acceleration at sea level. The ISP has therefore units of seconds instead of meters per second. The reason that we use this number, ISP, instead of VE directly is historical. It has been so many years around that we have become used to it, and people keep using it, in spite of the fact that dividing by G0 has no physical meaning here at all. As a rule of thumb, since G0 is 9.81, nearly 10, you can easily convert ISPs in second to exhaust velocities in meters per second by multiplying by 10. So for example, a rocket with an ISP of 300 seconds has an exhaust velocity of approximately 3,000 meters per second. In summary, we have learned about the Tsiolkovsky rocket equation and the interplay between the delta V of emission, the specific impulse of a rocket, and the rocket mass ratio. These ideas will accompany us on the rest of the course, so please make sure that you have a good understanding of them before continuing with the next video. Thanks for watching.